Hello friends, welcome. If you're interested in the cloud, but you're not sure what it can do for you, this module is for you. In this module, we'll take a high-level look at what cloud computing is and how it can help organizations around the globe. We'll first introduce what cloud computing is and what are the advantages of cloud computing. And we'll also look at the different deployment models and types of services and where each one is more beneficial. We will also compare services and technologies from different cloud providers. So by the end of this module, you'll really be familiar with what cloud computing is in general, and you'll be able to identify in which deployment model or type of cloud a workload best fits in. So why we need a cloud computing? Let's start with an example. When you are at comfort of your home and you need a light, what you do? You simply turn on a light and you simply expect light to work. A back of your consciousness, you know your home should have an electricity connection, but the details of how electricity gets into the light bulb are not important. You don't think about how electricity is being generated in the power plant, how it is traveled through a large network of high voltage transmission lines to your town, going to a substation and eventually making its way to your home. All this complex infrastructure and process is hidden behind a simple act of flipping a switch. Now just imagine if each house has to maintain their own electric power plant. We all have to buy, maintain, and run our own power plant infrastructure. Isn't it daunting? Believe it or not, 10-15 years back, we were doing same in terms of company data centers. Yes, I'm serious. Let's see how. If we actually look 10-15 years back, in each company's data center, we had a ton of servers, and each servers had a different purpose, maybe running on a different hardware, and even with different operating systems. Each new application that you installed, the vendor required that their application run on a dedicated server. Each one of those servers had their own CPU, RAM, and hard drive resources. And each one of them needed enough resources for utilization at peak time. But what this did is that on average, most servers were really underutilized. And organizations were spending a ton of money on hardware that most of the time was not even used at 10% of its capacity. We then started to implement virtualization, which allowed us to run multiple virtual machines on a virtual host, so we were able to get more usage out of our hardware and cut down space and cooling and of course the cost. In context of our electricity example, it is like a small community of 10-15 houses maintain one power plant. But still, they all together have to maintain a power plant. So virtualization was better than having individual machine for each application, but still there were a few disadvantages. We need to invest a lot in the hardware, the high upfront cost. And then we still need to pay for space in the data center. We need to pay for electricity, utility cost for cooling and all other server needs. So virtualization is really a lot better than dedicated hardware, but there are still space for improvement. And this is where cloud computing comes in. Now coming back to our electricity example, and we use electricity just as a utility, and it has three main benefits. First, you only pay for what you need. For example, we don't pay to our electricity provider some kind of upfront money for how long we possibly use electricity. Instead, we just pay the money against the amount of electricity that we actually use. Second, we don't worry about how or when power plant upgrade to the latest technology. It is all taken care by the government. And finally, we don't have to manage scaling the electricity. For example, people may move in or out of the town or tomorrow maybe your friends, your family, your relatives can come into the town, and it is electricity department responsibility to make sure that they generate and provide enough electricity for everyone. And all we are assured that our lights will stay on. Now, companies were looking for exactly similar solution for their data center and other infrastructure. Companies were looking for some solution where they can use compute and data storage in somebody else's data center so that they don't have to manage hardware or they don't have to do the maintenance. Companies were looking for some solution where they can easily expand their data storage, computation power, and other kind of scale which they need without having to invest capital in hardware. And companies were looking for some solution where they will pay only what they use. And this empowers the small companies to try different ideas and pay only what they use. Luckily, there's a solution to all these problems, and that is cloud computing. In the cloud computing, the word cloud is used as a metaphor for the internet. So the phrase cloud computing means a type of internet-based computing. In simple terms, I can say that cloud computing is like renting IT resources, just like electricity, where one company is renting a resources like virtual machine, storage, or an applications by cloud provider. The company providing these services is referred to as cloud provider. Some example providers are Microsoft, Amazon, and Google. So for example, Gmail and Google Drive are one type of cloud services provided by Google company, which can provide it free to certain limit, but we can pay and use more storage if we need to. So in simple terms, cloud computing is on-demand computing resources delivered to you over the internet. I repeat, cloud computing is on-demand computing resources delivered to you over the internet. In the cloud environment, you have cloud provider, which owns the data center and manage all of the hardware like server, networking, and of course, virtualization. And all of those resources are pulled together and then shared to multiple clients that all consume the same hardware. So these clients do not need to know that on what servers they run on or how many servers their different environments are running on. They simply consume a service, and the cloud provider is the one making sure that there are enough shared resources to handle everything. In the cloud environment, users simply select what services they want to use, with each service having a price per user or per minute of utilization of that specific resource. So let's learn some of the top benefits of cloud computing. With cloud computing, you don't have to buy expensive hardware. You don't have to buy software licenses. You don't have to set up and run on-site data centers. You don't have to maintain the racks of servers, the round-of-clock electricity for power and cooling, the IT experts for managing the infrastructure. And now because there is no wait for computing resources, you don't have to order a physical server and wait weeks for it to be delivered and installed. You could instead, through your browser, ask for virtual machine or database or something, any resource, and have them available within few minutes. In a cloud model, services are built on demand, by the minute, by the hour, or even by the second, depending on what services you are using. This on-demand billing allows organizations to create resources when needed and then stop paying for them when they don't need them anymore. Most cloud computing services are provided on-demand resources. So even vast amount of computing resources can be provisioned in minutes. Typically, with just a few mouse clicks, giving businesses a lot of flexibility and taking the pressure off for capacity planning. You can increase or decrease the resources and services used based on the demand and workload at any given time. As your workload changes due to a spike or drop in demand, a cloud computing system can compensate by automatically adding or removing resources. No maintenance. When you use the cloud, you are able to focus on what actually matters, building and deploying applications. Cloud usage eliminates the burden of maintaining software patches, hardware setup, upgrades, and other IT management tasks. All of this is automatically done for you to ensure you are using the latest and greatest tools to run your business. For example, if a disk fails, the disk will be replaced by the cloud provider. If a new hardware update becomes available, you don't have to go through the process of replacing your hardware. The cloud provider will ensure that the hardware updates are made available to you automatically. Self-service. And then the cloud is self-service, meaning there's a reduced need for IT experts. So let's say that I need a brand new web server and I'm going to run it in the cloud. Now I don't have to go to talk to my IT manager. I don't have to talk to a server admin. He doesn't have to speculate about the server, order it from, let's say, HP or Dell, and get the server, rack it, stack it, and hook it up with the UPS, connect it with the network, install the operating system, install the web servers, install the database, and then maintain and upgrade it forever. With the cloud, I don't need any of those people. I don't need to consume their time, which cost the company money. I just simply, with a few mouse click, provision a web server, and I'm able to run my application that I need to run. I put it on my credit card. I pay a few cents per minute to consume it, for example, and I can scale up, add as many more web servers as I need. And when I don't need them, I can simply delete them and take them off my account. Next is a global. Cloud providers have data centers located in various regions all over the globe. This gives you a local presence close to your customers to give them the best response time possible, no matter where in the world they are. And you can replicate to different regions. New solutions possible. You don't have to buy servers and hope that whatever you're doing, your projects or your startup or whatever, has to be successful. You need not make that large upfront investment before you can do things. Instead, you rent what you need, and if the project succeeds, great, and if it doesn't, just shut things down and stop paying. This lower financial risk for new projects means that you could do more innovation. You can take more chances because you're spending less on your attempts. That's a big win. And it's a big reason why cloud platforms have helped create a boom in IT startups that we have seen in the last few years. So cloud computing makes running a business easier. It's a cost-effective, it's scalable, it's elastic, it's current, it's reliable, it's secure. And this means you are able to spend more time on what matters and less time the managing and underlying details. Thank you. Now that we have looked at what the cloud is and advantages of cloud, let's learn what are the different types of cloud deployment models. A cloud deployment model defines where your data is stored and how your customers interact with it. How do they get to it? And where do the applications run? So we have three different types: public, private, and hybrid. The first one, and probably the most popular one, is the public cloud. In this case, we have no local hardware to manage or keep up to date. Everything runs on your cloud provider's hardware. You simply use your browser and access service and share the same hardware, storage, and network devices with other organizations. So in this case, your service provider provides the maintenance and you don't have to worry about it. You have near unlimited scalability. On-demand resources are available to meet your business needs. High reliability. A vast network of servers ensure against failure. Not all scenarios fit the public cloud. Here are some disadvantages to think about. Less control. You don't own the hardware or services and cannot manage them as you may want to. So for example, you want to deploy a web application or a blog site on hardware and resources that are owned by a cloud provider. Using a public cloud in this scenario allows cloud users to get their website or blog up quickly and then focus on maintaining the site without having to worry about the purchasing or managing or maintaining the hardware on which it runs. Private cloud. This is very close to traditional data center model we always had. In a private cloud, you create a cloud environment in your own data center and provide self-service access to compute resources to users in your organization. This offers a simulation of a public cloud to your user, but you remain completely responsible for the purchase and maintenance of the hardware and software services you provide. This approach has several advantages. First of all, there is no legal obligation. You can ensure the configuration can support any scenario or legal requirements. You are in complete control. You have control and responsibility over the security. Private clouds can meet a strict security compliance. And some of the reasons team move away from the private cloud, are infrastructure cost. You have some initial setup cost and must purchase the hardware for setup and maintenance. Difficult to scalable. And owning the equipments limit the agility. To scale, you must buy, install, and set up new hardware. IT skills. Private cloud requires IT skills and expertise that's hard to come by. A use case scenario for a private cloud would be when an organization has data that cannot be put into the public cloud, perhaps for legal reasons. An example scenario may be where the government policy requires specific data to be kept in country or privately. A private cloud can provide cloud functionality to external customers as well, or to specific internal departments such as accounting or human resources. Next up, we have the hybrid cloud, which is the combination of both the public and the private cloud, with automation and orchestration between the two. Hybrid cloud allowing you to run your applications in the most appropriate location. For example, you could host a website in the public cloud and link it to a highly secure database hosted in your private cloud or in on-premises data center. So some of the advantages of a hybrid cloud are you can use your own equipment to meet security, compliance, or legal scenarios where you need to completely control the environment. And some concerns you'll need to watch out for are it can be more expensive than selecting one deployment model since it involves some upfront cost, and it can be more complicated to set up and manage. This is useful when you have some things that cannot be put in the cloud, maybe for legal reason. For example, you may have some specific pieces of data that cannot be exposed publicly, which needs to be held in your private data center. Another example is one or more applications that run on old hardware that can't be updated. In this case, you can keep the old systems running locally and connected to the public cloud for authorization or storage. Now that we have looked at the types of deployment models, there are also different types of computing services. The three main ones are infrastructure as a service or IaaS, platform as a service or PaaS, and software as a service or SaaS. Let's take a look at what the differences are. What really differs between the deployment models is how much you manage versus how much vendor manages. Let's understand this with an example. Let's compare the difference between our own car, rental or leased car, taxi, and bus. This is exactly the difference between IaaS, PaaS, and SaaS. Traditionally, on-premises is likable to owning your own car. You manage everything from top to toe. from registering for the car, for maintenance, for upgrades, everything. IaaS is similar to renting a car. When you rent a car, you choose what to do with it. However, the car does not belong to you. And if you feel like an upgrade or change the car, you can do so very easily. PaaS is like taking a taxi or Uber drive. You don't drive the vehicle yourself, but you still need to navigate and instruct the driver what to do. SaaS is like taking a bus. Buses have assigned routes, and all you have to do is just hop into it and just take a ride, knowing that you will reach your final destination because the driver knows what to do. Now let's have a contrast of this with cloud services. Let's start with on-premises, where it's pretty easy. You are the one that manages everything from storage to the data center to networking or virtualization and application, everything. And then we have infrastructure as a service, which is the most flexible category of cloud services. This is really where you get provided the bare infrastructure you need to create your own computing environment. Instead of buying hardware with IaaS, you rent the hardware. Think about virtual machine, hard drive storage space, networking, and IP addresses, and those sort of things. So you can build an environment similar to what you have maybe built on your own data center or with the hosting provider. It aims to give you complete control over the hardware. It is like leasing a car or renting a car. The car, you have the complete control on the car, but still you don't own the car. And then platform as a service provides a framework for developers that it can build upon and use to create or test and deploy customized applications. The goal of PaaS is to help you create an application quickly without managing the underlying infrastructure. All servers, storage, networking is managed by the cloud provider, while developer maintains the management of application. So you don't have to worry about the patching or upgrade. Everything will be taken care of by the Microsoft or the cloud provider. All you have to focus is to how to develop and manage my application. It is like taking a Uber or taxi. You don't have to think about the registration of the car or the car have the proper gas and licenses and all. You focus where you want to go. You just let driver know. You get the navigation. You help driver to navigate to your destination. You don't have to think about the car itself. And our last option is software as a service, in which you simply enjoy the service. Pay a fees, but you don't manage anything at all. Everything is managed by the vendor. SaaS is software that is centrally hosted and managed for the end customer. It is usually based on an architecture where one version of the application is used for all the customers and licenses through a monthly or annual subscription. A majority of software as a service applications are run directly through the web browsers and do not require any downloads or installation in the client side. The most common example are things like the Gmail, where that's a Gmail or Microsoft Exchange in Office 365. So Gmail is like a software which is provided by the Microsoft. You can just use a browser and access that software. You cannot change it. You can just customize it according to your need and feel, but you cannot change the functionality of the Gmail. That is fixed. That is something which is designed and developed for everyone. It is like taking a bus. You cannot change the route. You can just get into the bus, pay for the ticket, and wherever bus is going, you can just go there. It may be close to your office. It may be a little far to your office, but you cannot change the route of the bus. And then after software as a service and infrastructure as a service and platform as a service, if you look out on the internet, you will find many other forms of cloud computing. In fact, I'm confident you'll find just about everything out there in some shape or form as a service. For example, you will find desktop as a service, where you can access virtual desktop in the cloud. You will find the backup as a service, where you can utilize backup service to protect your data either on or off premises. You will find the storage as a service, where you can simply store data out there in the cloud. There are many different forms of cloud computing, but SaaS, IaaS and PaaS typically encompass most everything out there. Though keep an eye out for these other types of cloud computing or other branding methods, if you will, to utilize this something as a service marketing terminology. Thank you. Companies who provide the hardware and services in cloud are called cloud provider. At this time, we have three main leading cloud providers: AWS or Amazon Web Services, Microsoft Azure, and Google Cloud Platform. Let's compare some of the services provided by them. So let's take an example of Amazon Web Services. AWS was the first real cloud platform, and it offers technology in all the areas I have just talked about. For IaaS, for example, Amazon Web Services offer Elastic Compute Cloud, EC2, or for PaaS, there's a primary service is Elastic Beanstalk. And for containers as a service, they offer the Elastic Kubernetes Service, EKS. As I mentioned earlier, all of the leading cloud platforms today support Kubernetes for working with containers. They also offer serverless computing, functions as a service with a service called Lambda. For data, Amazon Object Storage Technology is S3, the simple storage service. The primary managed relational service is RDS, the relational database service. And their primary NoSQL technology as a service is DynamoDB, although there are others as well. Another major player in the world for public cloud platform is Microsoft Azure. Azure also offers technologies in all the categories I have introduced so far. Their IaaS technology is called virtual machines, and their primary PaaS offering is App Service. For containers, Microsoft provides Azure Kubernetes Service, AKS, and for serverless computing, they have got Azure Functions. For object storage, Azure has blobs. For relational service, they have got SQL Server, and for NoSQL, there are various options with the Cosmos DB as perhaps the most visible one. The third major vendor in this market is Google with Google Cloud Platform. For IaaS, Google offers Compute Engine. For PaaS, Google offers App Engine. For containers, Google support Kubernetes Engine. And for serverless computing, function as a service, they offer Cloud Functions. For data, Google offers cloud storage for object storage, Cloud SQL as a managed relational service, and Cloud Bigtable for a managed NoSQL technology. Now, it is worth noting here that all three of the major cloud platform vendors have simple technology sets. This is no surprise. It's what commonly happens as the markets mature. Just a few years ago, these three offerings were much more different from each other. But today they have all worked out with the market, and so we have seen this convergence of services. That's why it is possible to think about the core cloud platform service in this simple grid like this. The three main cloud platforms, Amazon Web Service, Microsoft Azure, and Google Cloud Platform, get most of the attention in this area. But there are others, and they are worth mentioning. For example, Alibaba Cloud offers IaaS, object storage, Kubernetes, and a lot more. They offer a full suite of cloud service, and they are dominant player in China in particular. IBM Cloud also offers IaaS, object storage, Kubernetes, and a lot of other services. Interestingly, they also offer bare metal servers. You could actually rent just raw hardware from them. And there are a lot more. For example, many traditional hosters now offer some cloud services. The challenge though is that they don't have the scale of the market leaders. And so it's tough for them to compete in price and other areas. The key idea to keep in mind is that While the big three have the majority of the market share today, there are plenty of other small vendors in this market as well. Before finishing up this module, let's quickly review what we have learned so far. We have done an introduction to cloud computing, which allows organizations to consume computing services as a utility. The cloud brings us multiple benefits such as rapid elasticity of resources when needed. And since services are billed per second, minute, or hour, depending on the service, you can pay for services only when you need it, and also reduce that upfront cost of computer hardware. We have also looked at the different types of computer deployment model, the public, private, and hybrid, as well as the different types of service offering such as the infrastructure, platform, and software as a service. This is it for the introduction module where we really covered cloud computing in general. Thank you. Hello everyone. Welcome to this crash course on data warehouse. This module is designed for those who have no prior experience on data warehousing, but they are interested to learn Azure Synapse Analytics, or formerly known as Azure SQL Data Warehouse. Azure Warehouse is a big topic, and sometimes even a full-length course find it difficult to cover all the topics. So idea of this course is to understand basics of data warehouse concepts. In this module, you will learn what is data warehouse, why we need it, and how it is different from traditional transactional database. We will learn concept of dimensional modeling, which is database design method optimized for data warehouse solutions. Then I will explain what we mean when we say facts and their corresponding fact tables, and what are the dimensions and their corresponding dimension tables. How are these special kind of tables joined together to form a star schema or snowflake schema? This section will establish the foundation before you start my course on Azure Synapse Analytics, or formerly known as Azure SQL Data Warehouse. So let's get into it. Let's first figure out what we mean when we talk about the data warehouse solution. Long story short, it's another piece of software that does the following. Take data from several software programs used by a company like the accounting software or HR system, ERP or CRM systems, emails, different kind of Excel file with all different kind of information, flat files, and so on. Then it cleans this data, transform it, validate it, aggregate it, and puts it together in a smart way through a piece of process called ETL, which means extract, transform, and load. Then the integrated data is stored in a special kind of database that is called data warehouse, where data is arranged into a hierarchical groups often called dimensions and into facts and aggregated facts. And from there, data is presented in a clear format with filtering, slicing, and dicing capabilities. In reports, multi-dimensional database are a source for data mining activities, so that whoever looks into this information can easily draw some conclusions about the business process and ultimately make some decisions. Now, someone would ask the question, why do we need another piece of software that needs to be properly maintained? If I already have the data in my current systems, there's a feeling that a solution like this does not provide a lot of value since it just takes already existing data and stores it into a different location. And also, it maintenance cause a lot of overhead. Now, this seems a fairly good point of view, but recent history has shown us that in a company, getting the information you need from various systems can be a daunting task. If you think, what are the most common complaints for people who need to extract data from an operational system for decision making or for report purposes, there are quite a few. The quality of data that's being stored is overwhelming and hard to read. Therefore, it has no use. People who make decisions need to take only the essence from all the available data, only what's important. Showing somebody a 300-page report with all transaction details is not going to ease their job to figure out whether the company is losing the money or not losing the money. Showing them only one number with the total balance, having the possibility to go into more detailed data if they want to do that would make their life a lot easier. The data must be analyzed from all possible angles. What is hard to do by someone who is not an expert. Business people who usually are not data experts should be able to access data in an easy manner. How many times did it happen that managers from different departments have different numbers for the same KPI? That's something that should not happen because in the end, it is the same company. If people have access to the right data, they will report on the same figures. People should take advantage of the available data and make decisions based on the facts, not on assumptions. Changing with the organization's culture towards being more data-driven has proven to be a strategic decision that enables faster growth. Now, having identified the problems that can be solved with the data warehouse solution, we can translate them now into software requirements to be taken into account when designing a data warehouse. The fact that the system will be used by people who are probably not developers nor data experts means that the content should be easy to use and understand. The data presented should match the business user's vocabulary. The BI tools used for analyzing data from all different angles, which is sometimes we call slicing and dicing, should also be simple to learn and use. A BI solution should be fast. The query result should be returned to the user with minimal wait times. This is a sensitive subject because there's much controversy surrounding it. Sometimes you need to convince business users to have realistic expectations of what the BI system can do. If there are millions of rows of data that needs to be cleansed, validate, and converted into actionable KPIs, for example, this may take more than a few seconds. Sometimes it can take hours. Setting up the right expectations from the design phase is a very important step. Consistency is another important property of a data warehouse. The system must be credible. Before showing it to the user, we need to make sure that the data coming from different sources is processed, clean, and validate in the same manner so that the unified result, the end result, is consistent. For example, if the unit of measure from system is milliliter, but coming from another system is, let's say, ml, we don't want to have two rows in our dimension that have the same meaning, so we will make sure to insert only one of these values, preferably the one that's not abbreviated. We should create the system in such a way that it is to change it. Company strategies are changing fast, and with them, the user needs, business conditions, data and technology may also change. Other questions may need to be answered from data. The system should be designed to handle these changes without invalidating the existing data, report, and applications. Confidential information and other sensitive data is stored in a data warehouse solution. So controlling access to the system and securing it is a key requirement. And the last condition, but actually the core value of a BI system is to be the foundation for decision making. We need to show the right data to the users, and based on what they see are going to make business decisions. This is the most important purpose of a data warehouse, to enable people to come to conclusions and decide how to move forward with the business based on analytic evidence shown. It's not an easy task to design a good data warehouse system. And your responsibility as a data warehouse designer are quite a few. First, you need to make sure you understand who the business users are and what they need to know from a BI solution. You should create a persons who are going to use the data warehouse, describe the responsibilities, goals, objectives, and make sure that they match the real world people. You should also think of what kind of decisions they are going to make and what would be the best way to present data to them in order to facilitate better decision making. Not all data is relevant and even robust enough in order to be worth it to be included in data warehouse. If you are unsure that data is reliable, even after cleansing it, you need to address this issue and decide with the business how to improve the process and whether to exclude it altogether from the system. The output of data warehouse should always be accurate and trustworthy. You should also make sure that the user interfaces and templates used for analysis are simple enough and according to the corresponding user levels of expertise. And last but not the least, you need to be able to sustain the data warehouse environment. Make sure that the data warehouse runs smoothly and is loaded periodically. Update the system regularly with all new business requirements and keep the users happy. So these are the basic things to keep in mind while going through the rest of this course and also when you start designing your own data warehouse system. Thank you. In this lesson, I wanted to quickly touch on OLTP, means Online Transaction Processing System, versus OLAP, means Online Analytical Processing System. There are really some big differences between OLTP and OLAP. Let's discuss those. When I'm thinking about the database or OLTP, it's generally a huge number of very small transactions. Whereas when we talk about data warehouse or OLAP, I am thinking a low volume but very complicated queries. With OLTP, I am really focusing on current data. With OLAP, I am focusing on historic data, a data that is non-volatile, that's not going to change. With OLTP database, I am running my business. With OLAP database or data warehouse, I am analyzing my business. A database is containing highly detailed information. Every single aspect of that transaction is there. Whereas in the data warehouse, it's been summarized, it's been consolidated. When we talk about OLTP database, it's generally of gigabyte scale or maybe some terabytes. But when we talk about data warehouse, it's going to be a terabytes or petabytes of data. Or in nowadays, we generally think of a near infinite scale of system. OLTP system or SQL database is generally have performance limit. But when we talk about data warehouse, especially in cloud, we can pause or resume it. We can increase the scale limit. OLTP database is generally have ingestion limits. But when we talk about data warehouse, that is generally focused on something to run queries against at a massive scale, both in terms of data and in terms of complexity. Now, let's take a look at the technical aspect of a data warehouse and what they imply. I'm going to start with the dimensional model, which is database design, particular method which is optimized for data warehouse solutions. This has been introduced a few decades ago, but it is a very popular model, and because it addresses two important requirements of a BI solution. First is data is delivered in an understandable manner to the users, and also the performance of system is good. The data is retrieved from different sources, put together, improved, and loaded into a separate database in a process that's usually executed overnight. This way, the next morning, the users can access a freshly updated database that's optimized for read operations. The keyword for the dimensional model is simplicity. Simplicity of the architecture of the solution, and simplicity for the end users who can easily understand and process the data. Now, there are some concepts that are always used when we discuss about the dimensional model. These are the facts. Facts are numeric values that result from investigating the outcome of a business process. Example of fact is let's say the amount sold in the retail sales transaction. Facts can be combined and viewed in many ways with the help of dimensions. Dimensions provide a context of a business process. They are descriptors that define the facts. If the sales amount is the fact, then some dimensions could be the products that were sold, the customers who bought them, the store where the transaction happened, and maybe others. The attribute of a dimension provide you ability to describe data even more thoroughly. For example, if we want to analyze in more details the customers who bought items from a specific store, we can take a look at some attributes like their age, their gender, their address, and how far or close they live from the store. All of these attributes of the customer dimension, and what it means is that there are columns in the dimension table called customer. The star schemas are dimensional structures deployed in a relational database management system. They are not some independent objects, but they are the concepts. When you properly design a dimension model, a fact table together with dimensions will have a shape of a star. And we will discuss this more in next lesson. Now let's look at the practical example to understand these concepts better. Let's say you have interview with one of your client who wants you to create a BI solution, and they describe their activity as the following. We sell cake and other products in various locations, and we measure our achievements over time. Now, from this simple sentence, you can make some assumptions about what is important to analyze in their business. You can expand these assumptions with more details, or you can disprove them in the following interviews. But here is what you could assume for now. Products, locations, and time are obviously things that are important for analysis. These make a good starting point for defining the set of dimensions. Achievements is a generic word, but in this context, it may mean the sale amount or maybe the profit the company is making. So the model is simple, but it is great starting point for a real design. And as I mentioned earlier, simplicity is a key. So don't try to overcomplicate things from the beginning. A data model that starts simple has a chance of remaining simple at the end of the design. Let's start with the fact. Fact is a business measure. It can be measure of the sales, profit, volume, or maybe number of transactions. And a fact table is a table that stores a collection of facts that are similar. Facts answers the questions like what are we doing? And these questions later will be more complicated when we want to think about what we want to achieve. Each row in a fact table corresponds to one measurement event in real life. Most of the facts should be additive in data warehouse. Additivity is very important because BI applications contain fact tables with thousands and millions of rows and sometimes even more rows. And the most useful thing to do with so many rows is to add them or do some kind of aggregation on them to obtain some relevant value. So, for example, let's say if we have a store and if we store the item price as a fact. So, adding up multiple facts in this case would not have any real meaning. However, if we store the number of items sold as a fact, that will convey some meaning, that will add some value because we can add them now. And as far as item price is concerned, this is good for dimension table. So if you see the fact table by themselves do not provide a lot of value without some descriptors of the data. So what are the dimensions? If your facts are the transactions number and the sales amount, only from a fact table you can get the total number of recorded transactions and total sales amount. This is useful information, but you don't need to create an entire data warehouse solution for it. The actual magic comes when you start analyzing 4 dimensions. Each fact table is linked to a number of related dimensions through foreign keys. There is one dimension that should be present in almost all the data warehouses, and that is the time or date dimension. The data warehouse keeps track of the trends in time, and for that we need this dimension. The other requirement once are identified from the description of the business process. So now let's look at one example and see how easy it is to identify dimensions involved in the process. Let's continue thinking about the retail store. So we are going to think now for the steps performed by a customer of the store, and we will draw a fact table that keeps track of all the products being sold within a transaction. And of course, the date transaction was already identified. So think about, what do you usually do as a normal customer? You probably go to the store one day to do some shopping. You pick up the basket and start to select the products you need. When you're ready, you go to the cashier and they will help you check out your products and get your receipt. You select the payment method of your choice, maybe cash, card, some kind of voucher, or whatever. And then the transaction is considered closed. And then you are free to go with the merchandise you just bought. The beauty of the dimensions lays in the fact that they are obvious. You don't need complicated algorithms to figure out why the dimensions should be used in a process. So each fact table has foreign keys to the dimension table describing the business. When all the keys in the fact table correctly match the respective primary keys in the corresponding dimension tables, the tables satisfy referential integrity. You access the fact table via the dimension tables joined into it. The fact table generally has its own primary key composed of a subset of foreign keys. In Data Warehouse, every table that has a composite key is a fact table. And fact tables express many-to-many relationships, and all other are dimension tables. So to sum up, there are some of the most important characteristics of a fact table. First, there is one-on-one match between each row in the fact table and the real-world event. Most facts should be additive, although there are some who do not respect this property. A fact is linked to dimension tables through foreign keys, and the fact table has its own primary key, which is a composite key. Now, let's discuss the dimension. The dimensions are the companions to a fact table. And we say on the dimension table that it describes the context associated with a business process measurement event. This means that they answer questions like who, what, where, when, how, and why. All these questions associated with the event. Now, let's go back to the grocery store. When we thought about the steps of a normal shopping activity, we said that you put your products in the basket, do other steps, and then pay and then leave. But at this point, we don't know the name of the product that each customer bought or any other description about them. If we look at the product dimension table in more detail, we get to find out all kinds of useful information about the offers of the store. We can analyze by brand, by name, by category, subcategory, and so on. So now you get a lot more information about a specific transaction. This is what we mean by the descriptive context of a business process. There is no limit of how many attributes a dimension can have. You should not switch to performance tuning mode if you see a dimension with 50 or even 100 attributes at the same time. It is also not wrong to have dimensions that have only a handful of attributes. Dimensional tables usually have less rows than fact tables. although they can become much wider. So if you are designing a data warehouse having performance in mind, probably the dimensions will not be the bottleneck. A dimension table is defined by a primary key, which is going to be the reference in the fact table. And there are denormalized tables, which is also a reason for having so many attributes. For example, in the product dimension, we can include the category and subcategory of the product, maybe the department, and maybe some more information about the brand, and whatever other information related to product in the same table. This information would be spread over multiple tables in an operational database that usually normalized. In data warehouse, we put similar descriptors in the same dimension table. A dimension together with these attributes describe the business that you are analyzing. So every information that's relevant for analysis should be present in the dimension. However, it is a good practice to not overload your dimension with too many attributes because it is harder to use and chances are that not all of them are equally important. So what we discussed so far, if you put everything together, the fact table and the dimensions, the model looks like this. So what do you think about this model? The first thing I noticed is that it looks clean and simple. Where some will be disappointed by the simplicity, it is obviously an advantage because it means that the data is easy to understand and analyze. Each dimension is an equivalent entry point into the fact table. And this symmetrical structure allows effective handling of a complex queries. Another reason why this wonder is powerful is the fact that it's highly recognizable by the business users, by the people who are going to look at it every day. It does not take more than a few glances to recognize that this dimension model is actually their business. Finally, dimensional models are easily extendable to accommodate a change. If the business questions that need answers from the data warehouse requires a new dimension, it is simple to add to the model. You create a new table for it. Then you link the dimension to the related fact tables to make sure that the row in the dimension can be linked to the row in the fact table. And that's it. A dimension can be supplemented with the new attributes, and so can a fact table being enriched with the new facts. In the same way, we can add a completely new facts table and link it to the existing dimension table. Dimensional model implemented in relational database management systems are referred to as star schemas because of the resemblance to a star-like structure. The facts are in the middle and dimension tables are around the corner. So the model looks like this. Because these tables are already denormalized, so the only link between the tables are from the fact to the dimension. Another model using data warehouses is a snowflake, in which the tables still respect the normalization rules. This means that there are more dimension tables linked with the foreign keys because of several layers of dimension tables. This structure resembles a snowflake schema. So you have reached the end of this module, and by now you should have a better understanding on the theory behind data warehouse. Let's do a quick recap of what was presented in this module. By now, you should have a better understanding what is data warehouse and why we need it to present consolidated data to business. You have learned the difference between online transaction processing or OLTP versus online analytical processing OLAP. You have learned the fundamental concepts of dimensional modeling, database design method optimized for data warehouse solutions. You learned that facts are business measure like profit or volume, and fact tables store these business measures. You have also learned that dimensions are companions of fact table that answer questions like who, what, where, when, how, and why. And these information stores in dimension tables. And finally, we saw the difference between star and snowflake schema. Thank you. Hello friends, my name is Ishant Garg. This section is to cover basic concepts and understanding of Hadoop. Hadoop is a big topic and requires a full-length course in itself. So in this module, I will only cover what is essential to understand Azure HD Insight. If you are already familiar with Hadoop, please feel free to skip this section. We will discuss why our traditional systems can't handle the data requirements of today's world and how Hadoop is different from relational database management systems. We will also discuss fundamental understanding of the three main building blocks or components of Hadoop, like HDFS or Hadoop Distributed File System, the MapReduce programming model for processing, and the resource negotiator YARN for cluster management. We will also take a quick look at other components of Hadoop ecosystem. Thank you. In this video, we will try and understand why is it that we need a distributed computing environment. The amount and scale of data that we are dealing with in today's world requires distributed computing environment. We will see the role that Hadoop leaves in a distributed computing setup and also take a brief look at technologies which work along with Hadoop. It's often helpful to have numbers in order to get an understanding of how big is big data. We will look at Facebook and Google and see how much data they are dealing with. Facebook has 2.4 billion monthly active users and it generates 4 petabytes of data every single day. Similarly, Facebook now has over 100 million hours of daily video watch time and user generates 4 million likes every single minute. Now what about Google? As you can imagine, the amount of data stored by Google beats the Facebook. Google stores more than 20 exabytes of data. Google's core job is to download the entire internet. So this shouldn't be very surprising to you. Now there are more than 4 million searches happening every minute in Google. For comparison, there were only 10,000 searches per second in 2006 and now close to 65,000 searches per second, more than 6 times. This state clearly shows how the internet continues to change the way we live. Google has almost 4 million apps on Google Play Store and 300 hours of video upload on YouTube in every single minute. Google not only constantly download the new web pages, but also process the updated pages for search results. That's a huge data set. Both of these organizations deal with a data set which would have been unthinkable even 10 years ago. Now, if you think about a dataset like this, do you really think a single machine will be able to service this? However powerful that single computer is, it is just cannot deal with the data at this scale. Let's see what is it that we require from a big data system. It should be able to store massive amounts of data because the raw data itself is very huge. So there's a storage. That is first thing. Now, after storage, we should be able to extract useful information from these millions and billions of rows of data. So we need to process it in a timely manner. So we need a processing power. And finally, there's a third requirement. If you look at the trend in data usage by companies like this, for example, as we just discussed that Google search increased from 10,000 to 65,000 in last decade. Let's take one more example of LinkedIn. LinkedIn grew from 37 million users from the first quarter of 2009 to over 600 million users today. Now, to keep up with the data that grows at this rate, you need a special kind of system. The infrastructure itself should be flexible such that as the data grows, you can increase storage and you can increase computing capacity without completely reworking your system. So the big data system that we build needs a scale. Storage and processing capacity are useless without the ability to grow them as data grows. Big data system requirements cannot be met by traditional technologies. They don't cut it anymore. In order to get all the characteristics that we require from our system, we need a distributed computing framework. And this is where Hadoop comes in. Any system which performs computations for us can be built up in two ways. A monolithic system, where everything is on a single machine and in one big chunk. Or a distributed system, where there are multiple machines and multiple processes which run on these machines. In exactly the same way, there are two ways to build a team. For example, a football team. Your team can have a star who probably dribbles and endure. So you have one star who does the heavy lifting. Or an entire team of good players, none of whom are stars, but all of them work together really well and are really good at passing the ball. This is exactly equivalent to a supercomputer and a cluster of machines. Two ways to build a system. The monolithic way is equivalent of one star player that you really rely on. That one player does everything. A monolithic system typically is a single powerful server, and if you want more computing resources and capacity from the server, you might be tempted to pay twice the expenses to improve the performance of this machine. But you will get less than 2 times the performance. The performance of a single machine does not scale linearly with cost. On the other hand, if you look at a distributed system, the equivalent of a team of good players who know how to pass the ball and work together really well. These distributed systems are made up of typically commodity hardware which can be used to parallelize the tasks. Here, the onus of improving performance does not lie with one single machine. It lies with all the machines which work together. The players on this team, the individual machines, are called the nodes, and the entire system is called a cluster. No individual node in this cluster of machines is a supercomputer. They all tend to be cheap machines or commodity hardware, but they come together as a team to solve your data processing needs. Something that is axiomatic today but was not really well known 15 or 20 years ago is the fact that a cluster of machines can scale linearly with the amount of data that you have to process. The capacity of such a cluster increases with the number of machines in the cluster. If you double the number of nodes that exist in the system, you will get twice the storage. That's pretty obvious. Each machine comes with its own hard disk, and doubling the number of machines doubles the storage capacity. What makes such a distributed cool is that you can achieve computational capacity or performance that is twice what you originally had. When you double the number of machines, you get nearly twice the performance, twice the speed. A distributed system satisfies the third critical requirement in big data processing. Keeping up with the ever-increasing amount of data that we have to process at any point in time. And this is the reason that companies such as Google, Facebook, Amazon, or Microsoft build these vast data centers that are populated with hundreds and thousands of machines. These server farms, all these machines which live in these server farms, are where actual processing of data takes place in parallel. Now, we need something in order to have all these machines work together in a way to solve a single problem. These servers need to be coordinated, and it is a software which will perform this coordination. This is a special piece of software which takes care of the needs of a distributed system, things like partitioning data, so that any data is stored across multiple nodes in a system. This data is protected against loss by replicating the data on more than one node or coordinating compute tasks. You might have a task which runs in parallel on multiple machines. This software will ensure that all these processes run through to completion successfully and store their results in a correct place. It also needs to handle fault tolerance and recovery. Each individual machine is not a great system by itself. It's a commodity hardware, which means it's prone to failure, disk failures, node failures. All of these needs to be handled. In order to run a process, this software needs to ensure that a particular node has the resources required for the process to run in terms of memory, compute capacity, hard disk space, etc. Distributed computing, which coordinates so many machines together to achieve one objective, adds a huge overhead and complexity to any processing task. Individual developers who work on this distributed system cannot focus on the nitty-gritty of the actual cluster management. That's where the software comes in, to abstract developers away from the details. As we discussed in previous lesson that working with distributed systems requires special software which explicit purpose is to coordinate and manage all the processes and machines which exist within the distributed system. Back in the early 2000s, as Google web search was getting more and more powerful, Google realized that the traditional software, traditional methodologies would not work for this scale of web search. That's when they realized that they would have to build something of their own to manage all these processes, which can run on hundreds of thousands of machines. Google developed proprietary software to run on these distributed systems. What were the objectives of this proprietary software? The first was to store the millions of records across multiple machines. So keeping track of what record existed on what node within the data center was one part of the problem, which the software had to solve. The second part was how do we run processes across all these machines and coordinate these processes in such a way to achieve a single objective. This was the most important problem that Google engineers worked on back in the day, and then came up with two systems to solve this problem. One was called the Google File System, and the other was called the MapReduce. Google File System was responsible for storing data in a distributed manner. It was a file system which existed not on a single machine but on multiple machines which made up a cluster. This would solve the distributed storage problem. MapReduce was used to solve the second problem, the problem of distributed computing running processes in parallel across multiple machines to take advantage of the inherent parallelism in data crunching tasks, and bringing the results of these processes together to achieve something useful. Google engineers developed these technologies and then published paper talking about how these help in distributed computing. These papers were, of course, available to all other engineers who had been working on similar systems. Engineers working on distributed computing framework adopted these principles based on published papers from Google and then developed the core of what is today we call Hadoop. So the equivalent of Google File System is HDFS, and the equivalent of MapReduce programming framework that Google has is called MapReduce. HDFS is the Hadoop distributed file system, and MapReduce is the programming module for parallel processing. HDFS plus MapReduce gives us the Hadoop that we know today. HDFS is the file system which manages storage of data across machines in a cluster. MapReduce is a framework to process data across multiple machines. Hadoop is distributed by Apache Software Foundation, and it's open source, which means there are thousands of engineers who have contributed actively to Hadoop, and it happens even today. Hadoop constantly undergoes improvements, and in 2013, Apache released a brand new version of Hadoop, Hadoop 2.0. This was a fundamental change where the MapReduce framework, which was responsible for processing data across machines, was split into two logical components, MapReduce and Yarn. The responsibility of each of these components was made narrow and more focused. The MapReduce framework was now only to define the data processing task. It was focused on what logical operations you want to perform on the raw data that you have. Yarn was the framework to run the processing task across multiple machines, manage resources, manage memory, manage storage requirements. Yarn did not care what the data processing task was. That was under MapReduce. Yarn only was responsible for running it and seeing it through to completion. These three components, HDFS, MapReduce, and Yarn, have corresponding configuration files. These are the basic building blocks of Hadoop. So whenever anyone talks about the block diagram of Hadoop, these are the logical components. You have a processing task which you want to run on the cluster, which has Hadoop installed. What exactly is the series of steps that happen when you submit a job to Hadoop? The first thing is for you to define map and reduce tasks using the MapReduce API. This is available to work within Java and also other programming languages. This defines what computation you want to perform on the data. MapReduce programs are packaged into jobs, and Hadoop cluster deals with jobs as a whole. A job is triggered on the cluster using Yarn, and Yarn checks whether the cluster or the nodes in the cluster have resources in order to run this job. Yarn then figure out whether this job is supposed to be run and then run the job and store the data, which is the result of the job, in HDFS, the storage system. This is a typically life cycle of a MapReduce, which is running parallel across multiple nodes in a cluster. Let's see some difference between Hadoop and RDBMS. The first one is structured versus unstructured data. First of all, there's the nature of data structure with RDBMS. The data is absolutely structured. With Hadoop, it's all unstructured data across the HDFS file system. So you have got essentially no schema. You can project structure on that unstructured data in a number of ways using Hbase. For instance, writing Hive queries. The idea here with Hadoop is what's called schema unread. So you are developing the schema as you are doing the processing operations on the data. Whereas the SQL database and data warehouse, the schema is always present there as a skeleton. The next one is the cap versus ACID properties. Relational database management systems ensure data integrity through transaction through ACID properties. ACID, ACID stands for atomicity, consistency, isolation, and durability. In contrast with the big data like Hadoop, we have what's called the CAP theorem: consistency, availability, and partition tolerance. Now, consistency is not Hadoop's biggest point. It's not, generally speaking, an interactive environment because, again, you're dealing with potentially huge scales of data that's completely unstructured. So you have data with different context, data that has different properties, different use cases. But certainly availability is a huge point of Hadoop because you have spread your data across a number of nodes. And we are going in next module that HD Inside adds another layer of availability because you are separating the cluster. Next is data throughput. Normally in a on-premises Hadoop environment, the HDFS is actually part of your cluster. But HD Inside can decouple the storage and compute layers, which means you can bring your Hadoop clusters online or destroy them, which is a good thing from a cost-saving perspective. Query performance. Generally, relational systems offer a lower data throughput but faster query performance. It's lower because, especially in the case of systematic multiprocessing systems like Azure SQL database, you have got just a single virtual server. So computers are bottlenecked. But in contrast, Hadoop, that's distributed across the nodes in a cluster. You have got potentially much higher data throughput. But because MapReduce has to map across all the nodes to round up the data that you are requesting in the query and then distill it down, reduce that result set, that's going to give you potentially much lower granular query performance. And then scaled. RDBMS is our vertically scaled and Hadoop is horizontally. That's similar to Azure SQL database versus Azure SQL data warehouse. And RDBMS, as we know, is online transaction processing platform, whereas Hadoop is more for Olap. And finally, cost. The SQL Server product is, are all licensed enterprise software products that are closed source. Hadoop, by contrast, is mostly free and open source. I say mostly because the companies like Cloudera and Microsoft that offer managed version of these open source tools. And you're paying for the premium experience of having not only a hosted environment, but in the case of like HD Insight, integration with the entire Azure ecosystem. As we discussed in the previous lessons that how Hadoop and equivalent Google proprietary system completely revolutionized distributed computing. As distributed computing become more than the norm rather than the exception, people realize that the use of Hadoop and the distributed computing environment should not be restricted to hardcore developers in Java. It should be made more demographic. People with different skill sets ought to be able to use the power of distributing computing. This is what led to the rise of a whole ecosystem of tools which work with Hadoop. Some of the most popular technologies that you might have heard of are Hive, which gives a SQL-like query interface to data stored in a big data system. Hbase, a NoSQL database. Pig, a way to convert unstructured data into a structured form. Uzi, a workflow management system. Flume and Scoop, tools which allow us to put data into Hadoop and get data from Hadoop. And finally, Spark, a way to perform a really cool complex transformations in a functional way on big data. Let's take a brief look at all of these in order to understand where they fit in and how they help make data processing more demographic. Hive. Hive is a SQL interface to Hadoop. Traditionally, people from analytics backgrounds are very familiar with relational databases and SQL. But in a big data system, they need to program in Java, which they may not be comfortable with. However, Hive gives a bridge to Hadoop for folks who do not have exposure to object-oriented programming in Java by converting their SQL-like queries to MapReduce behind the scene. The user writes queries which runs in the background in a MapReduce programs. Hbase. As big data systems become more prevalent, people realize that you needed a way to perform low latency operations on your database. HDFS is a batch processing system. Hbase was built on top of HDFS to allow low latency operations on key value pairs. Data in Hbase can be looked up and scanned very quickly indeed. It's essentially a database built on Hadoop. Pig is a scripting language which allows us to take data in its extremely raw and unstructured form. Think log files where there is absolutely no structure to the data. It's just a lines of messages, warnings, etc. It manipulates this data and converts it into a structured format. This structured format can then be stored in HDFS or in Hive and then can be queried by people looking to extract information from it. Pig can essentially take data which looks unusable and convert it to a form which is actually useful. Now Spark, one of the most important one. Spark is a technology that very much involved nowadays because of how easy and simple it makes working on big data sets. You can change and transform huge data sets and extract information with it in a very interactive and iterative way. It's essentially a distributed computing engine built on top of Hadoop. It has an interactive shell either in the Scala or in the Python, which allow you to quickly process data sets. You can simple type in a bunch of transformations and see what the result look like in Spark. It's very fast and it has a whole bunch of built-in libraries for machine learning, stream processing, and graph processing. And its a framework includes all the useful tools that you will need with a big data system. Organizations like Google, Yahoo, and Facebook doesn't just run processes of one type. They have a chain of processes constantly munching data. Managing all these processes requires a workflow management system. And that is what Uzi is all about. A workflow management system which works with all Hadoop technologies. And with this, we come to the end of this module on Hadoop overview. Hopefully, you have understood why we need a distributed computing system and why it is superior to a single computer setup. You have also understood what role Hadoop plays in a distributed computing setup and why technologies like Hadoop was developed in the first place. You also have some big picture understanding of various technologies which live within the Hadoop ecosystem and are built on top of Hadoop. Thank you.